This problem has us find the response of the system, that is x1 and x2, due to an initial condition. So we are just trying to find what I will call x of t as a vector, which is x1 and x2. So in the system, we have two masses, we have two springs. We're told to ignore the gravitational potential. There's not going to be any damping to consider, and there is no external forcing. So we're considering the vertical motion of m1 and m2. And if we look at how the system is put together, if we hold x1 to 0, so hold m1 still, we can move m2 up or down because it has a spring connection to m1. It's not rigidly connected. Also, if we hold x2 at 0, x1 can change even if x2 is held still. So this tells us that x1 and x2 are independent degrees of freedom. Just because we know the value of one does not mean we automatically know the value of the other one. So this will be two independent degrees of freedom when we go into our modeling. So I'll use Lagrange's equations to get the equations of motion, or the matrix equation of motion, out of this. So in terms of the kinetic energy, we have m1 and m2 are going to have translational kinetic energy only. They are not able to rotate. They are only able to individually move vertically. And nothing else in the system has mass or inertia. So we have 1/2 m1, and the velocity of m1 is x1 dot. So that gets squared. For the velocities, we use their absolute velocities. Since x1 and x2 are being measured from this inertial frame, x1 dot is the velocity of m1. There's not a relative velocity in terms of our kinetic energy. So that means that m2, its velocity is x2 dot, and that will get squared. All right, now that's all for the kinetic energy. Now we can look at the potential energy. Two things are going to have potential energy, k1 and k2. We are ignoring the gravitational potential of the masses, as we typically do in these problems. We have nothing else deformable besides the springs. So let's start with spring 1, which is k1. So the deformation of k1, we see at the bottom it's attached to x1. At the top, it's attached to 0. It's not able to move at the top, or what's called the base there. So we can say it's k1 times x1 quantity squared, or just x1 squared. Now, because only one side of it can move, that's like we've been seeing in the 1 degree of freedom problems. It's k2 that's just going to be a little bit trickier, because the bottom of k2 is attached to x2, and the top of k2 is attached to x1. So we need to find its net deformation. Because again, if x2 and x1 are equal, x2 is in pure translation mode. It's not being stretched or compressed. It is moving, but it's not changing its length. So we need the relative displacement of the two ends. So what we can do is, in these parentheses, we can think for the two ends, what sign on the two ends, on each of them, would cause it to be in tension. I think is an easy way to figure out what the inside should look like. So we can say, all right, x2 being positive, we'll put it into tension. That is to say, if x1 were held at 0. And if x2 were held at 0, then a negative x1 would cause it to go into tension. So we need to be careful on the signs here. So either we can think of the sign on each that would cause it to go into tension when the other side was held still, or the sign on each that would cause compression if the other side were held still. But to keep in how we were thinking about it for system dynamics, I like to think about the tension and what sign would cause that for this. That way we can calculate this relative or net displacement much easier. And I will rewrite this just to make the differentiation step a little bit easier by expanding out this difference of squares, or the square of a difference. So we're going to get x2 quantity squared minus 2x1 x2 plus x1 quantity squared. And then the outside I'll just leave with that 1/2 k2. We have no dissipation, so our R is 0. I'll still keep track of it here just to make sure that we remember to look at that. All right, so finally, and I'll leave this in the modeling step, I'll do the Lagrange equations. Now we have two independent degrees of freedom, x1 and x2. So the first Lagrange equation, I will take del t del x1. I'll need the time derivative of that on the outside, plus del v del x1, this should be x1 dot, equals, and this is an autonomous system, so 0. And let me resolve this first before I go on. All right, so let's look at del t del x1 dot. This one is pretty straightforward. The first term in t has that x1, so the 2 comes down and we are left with m1 x1 dot, and then we take the time derivative and that gives us the double dot. Now the del v del x1. So we go down to the v equation. The first term has an x1 in it, so we are going to have a k1 x1. And then when we go to the second term, we have an x2 squared. Well, that just goes away. We have a negative 2 times x2 will be its partial derivative, times the 1/2 k2 is going to leave us k2 x2, and that will be negative. And then the last term, we have an x1 squared, so that is going to leave us with plus k2 x1. Right, so again, we have 3 terms here after we differentiate v with respect to x1. So the first term, and then in that second collection of terms, we're left with that mixed derivative, or that mixed x1, x2 leaves us the negative k2, x2, and then plus k2, x1. And I will rewrite this by grouping my degrees of freedom together, because we see here we have 2 terms with an x1. So I will factor out the x1 minus k2 x2, and the right-hand side is still 0, is 0. All right, so that is our first equation of motion. I will rewrite it in the equation of motion step in matrix form. Now our second equation of motion comes from doing the same process, but with the other independent degree of freedom, x2. And our right-hand side, still 0. All right, so we differentiate t with respect to x2 dot. Going back up, that's going to give us, this is going to look very similar, m2 x2 double dot. And now we differentiate v with respect to x2. And we're going to get, the first term will go away. There's only an x1 in it. And then we'll have a k2 x2 from differentiating that x2 squared. We have this mixed expression again. So the x2 will go away this time, and we will be left with negative k2 x1. And then the x1 squared goes away because it has no x2's in it. And that's what we get for our second equation. And I'll rewrite this just to maintain the same order that we had before. So I'll put actually the x1 first, plus the k2 x2 equals 0. All right, so from our Lagrange's equations, we have the 2 scalar equations of motion when we differentiate with respect to each of our independent degrees of freedom. Now in my equation of motion step, this is where I am going to put them together into the matrix form. So again, we want it in the form of mx double dot plus kx equals 0 matrices, which I'll identify. So I have 2 equations of motion, so these will be 2 by 2 matrices. And there is no C matrix, or it's the 0 matrix, because there is no damping in this system. So that's why I'll have an M 2 by 2 and a K 2 by 2. So equation 1A, I just need to fill in the correct spots here. So M1 X1 double dot plus 0, just so we can see what it looks like, plus 0 X2 double dot is implied, but I'll put it explicitly there. And then the same thing here, I'll put here, oops, this will be a 0, x1, double dot. All right, but back to equation 1a, the x1 term has a k1 plus a k2, and then negative k2 times an x2, and then 0 on the right-hand side. The second row for our matrix will use 2a. So that implied 0, which I now wrote in 2a, and an m2 times an x2 double dot. For the stiffness matrix, I'll have a negative k2 is the x1 coefficient, and a positive k2 is the x2 coefficient, and the right-hand side is 0. All right, so just so it's clear, we have our M matrix, this 2 by 2 times an x double dot plus a kx equals 0. So we've identified the stiffness matrix K and the mass matrix M. Now I will put in numeric values, since that's what we're going to need to get our natural frequencies and our mode shapes. So start it algebraically and now fill in the numbers. So we are told, actually we have a lot of symmetry here, both masses are 20 kilograms, both spring constants are 1,000 newtons per meter. So that makes filling in our mass matrix easy. Will be 20, 0, 0, 20. And then for the stiffness matrix, we are going to have here 2,000, negative 1,000, negative 1,000, 1,000. And I'm working in base units here, kilograms, newtons, meters. Equation of motion is done. Now we can go into our identify step. So looking either at the algebraic or the numeric one of the equation of motion, we can tell we have two independent degrees of freedom. So it's a 2 DOF, linear. This is undamped, or conservative, or non-dissipative. And the right-hand side tells us it's free or autonomous. So the general solution to this problem is going to have the C1 chi1 cosine omega 1 t plus phi 1 plus C2 chi2 cosine the second natural frequency times t plus phi 2. So if we can identify C1, C2, phi 1, and phi 2, omega 1, omega 2, and chi 1 and chi 2, then we can have our full solution for x of t. So that's what we can do next as we go into our parameter step. All right, so first thing we can do is we can get the natural frequencies using the eigenvalues of m inverse k, and then we can get the mode shapes using the eigenvectors. So let's get first our natural frequencies, and I'll do this in MATLAB. I'm not going to try to find the eigenvalues by hand here. Going into MATLAB, I can put all of my modeling parameters in and just double check the M matrix is correct, the K matrix is correct. That's the same thing we have. So now let's find the eigenvalues and the eigenvectors. So I'll start with the eigenvalues, since that's what's going to lead us to finding the natural frequencies. So if we take the eigenvalues of m inverse k, or in MATLAB m backslash k, we'll do the same thing. These are the eigenvalues of m inverse k, and remember the natural frequencies are the square roots of the eigenvalues. So that's what I can do in this next step here. I'll just run these two lines. So the natural frequencies omega n are the square roots. So the square root of the 19.1, we get the 4.37. And the natural frequency based on the square root of 130.9, we get 11.44. While we're here, we can also look at the eigenvectors, which will tell us the mode shapes. So again, that's going to be what I'm saving as v here. So we see the v that comes out. We have the first column, negative 0.526 about, negative 0.851, and the second column, negative 0.851 and positive 0.526. So in this case, they're actually negative reciprocals of each other, it turns out, and that's coming from the symmetry in the problem. That won't always be the case. But here it is. And just remember that the order of the eigenvalues is associated with the order of the eigenvectors. So the first column of V is associated with the 4.37 natural frequency, which comes from the first eigenvalue. And the second column of V is associated with the 11.44, coming from the second eigenvalue. So we can record these as these are going to be parameters in our system. So from MATLAB, I'll just write them down here, the two natural frequencies in ascending order. So they actually did come out in ascending order from MATLAB. So we don't have to rearrange them here. And I'll just keep 3 decimal places. So 4.36 and 11.4 radians per second are the two natural frequencies in our system. Chi1 is going to be the vector negative 0.526, negative 0.851, and the second mode shape Chi2, negative 0.851 and positive 0.526. So I'm just copying them right as they came out of MATLAB. The scale, again, won't matter as long as I maintain the same eigenvectors as I solve for my initial conditions. So notice like Chi1 has a negative and a negative. I can multiply this by negative 1, the top and bottom, and get 0.526 and 0.851, and that'll be fine. All it's going to do is reverse the sign on the C1 I'm going to find. So I can just use them as is, and I don't have to really worry about that. Now I still need the C1 and C2, which again I'll put here as placeholders because I need the initial conditions in order to find the C's and the P's. So I will come back to that, but I need initial conditions to get them. So we are told here, initially the displacements of x1 and x2 are positive 0.2 and negative 0.2 respectively, and we're going to not have any initial velocities. So just initial positions, 0.2 and negative 0.2. So x1 of 0 equals positive 0.2 meters. x1 dot of 0, the initial velocity is 0. x2 of 0 is the negative 0.2. And the x2 dot of 0 is 0. So these translate to our 4 algebraic expressions. So for the first one, we can actually write these in vector form, will be easier. So for our positions, our x of 0 is 0.2 and negative 0.2. And this gives us a vector equation, but really it's 2 scalar equations, C1 chi1 cosine of phi1 plus C2 chi2 cosine of phi2. Right, so this is coming from that x of t equation up here, our general form, evaluated at t equals 0, since that's the initial condition. So that's 2 of our equations. And I'll rearrange it in a second. And then our x dot of 0 is the 0 vector because it's initially 0. And that will be negative omega 1 c1 chi1. Remember, chi1 and chi2 are vectors. Sine of phi1 plus a negative omega 2 c2 chi2 sine of phi2. Get rid of that. All right, so these 4 equations must be simultaneously true. These 4 algebraic equations must be simultaneously true. So we have to find the C1, C2, phi1, and phi2 that make these 4 equations true. So again, we're going to use that fminsearch to solve it all simultaneously, because algebraically by hand this is difficult because we'll have the phis inside of trig functions. So using MATLAB and fminsearch is not the only way to do it. We don't necessarily have to do it numerically, but it will be easier. So the one thing I want to do to set it up to work with the fminsearch is I want the left-hand side to be 0 in both of these, which for the x dot it actually already is, but the general form, I'm going to subtract off this vector from both sides, and that will make this then 0. And these are the expressions I'm trying to make 0. So I'll just get rid of this, and we would subtract off 0, 0 just for good measure. This is what it's going to look like in MATLAB. So these are the equations that I'm going to put into the fminsearch to minimize, because when each one individually is 0, that means that I've satisfied the constants that make the initial conditions true. Back in the MATLAB, I define my x1, my position, and my velocity equations in terms of time and in terms of this constant collection of constants c. C of 1 is c1, c of 3 is my phi1, c of 2 is c2, and c of 4 is my phi2 by my definitions here. And then I put in my initial conditions, and now I am going to find my constants. So same method I used in the first example here. I want to minimize the square of each of the equations. So the minimum is going to occur when my sum of the squares is 0. That means that each one would be exactly satisfied. So we've seen this before, so I'll run it and just check the results. And I need my options here. Okay, so this is what we get coming out. This is the C value. So it says that C1 is 0.065, C2 is negative 0.275, and the phis are 0. Again, because our velocities initially are 0, that's going to be typical, is that our phases will also be 0. And then we can check our f, the value of that function. Ideally, perfectly, it would be equal to 0. It's not. It's a very, very small number, though. And we see that the flag is 1, meaning that we did have convergence. So these two indicators mean that the constants that we found should be pretty good, that we're not going to get much better than those. If I rerun it, we're going to get the same results again. So copying down those values we have from MATLAB, our C1 we found using fminsearch 0.065, and C2 was a negative 0.275. And both of our phases, our phi1, phi2, we got 0 radians out of that. Now we have our omegas, our chi's, our c's, our phis. We can now assemble our full solution. So our full in matrix form solution or vector form solution is going to be, we have C1 times chi1. We can combine those. And we're going to get then negative 0.0342 and a negative 0.0553. And that will be times the cosine of our first natural frequency, which was 4.36 times time, plus our first phase, well, phi1 was 0, so I don't need to record that here. Plus, now this is C2 chi2. We get 0.234 times a negative 0.145 times the cosine of the second natural frequency, 11.4 times time, plus phi2, which again is 0. So here in vector form is the solution for x1 and x2. x1 of t, again, is that top row, and x2 is going to be the bottom row. And if we look at the relative strengths, let's look at the top row first. We see that the second, this 0.234 is much larger than the negative 0.0342. So relative magnitudes, we should expect for x1 that the faster oscillations are going to be more pronounced. And actually the second for the second equation, that should be true too for x2, that the negative 0.145 is going to be about 3 times or so larger than the first one. So we should also see more amplitude in the faster oscillations than the slower for x2. So we can plot it and we see what the case is going to be. So now I'm going to take everything, apply my initial conditions, find the C's and the P's, and I'm going to plot the results for x1 and x2. And when we do that, we see our results here. So for x1 in red and x2 in blue. So first we can check, just to double check that we did things right, or we probably did things right, let's look at the values at time is 0. Make sure that it matches our initial condition. So for x1, we get a value of positive 0.2. So that's good, that was its initial. And for the blue one, x2, we get negative 0.2. So at least our initial conditions match. So that's a good sign. And we see here that the peak of x1 and the valley of x2 appear to happen at the same time. If we drag this up and try to find the peak, and we try to find the valley here. So both of them at 0.286. Well, this is 6.8. It's a little bit off. But more or less the peak of one is the valley of the other and vice versa. So these two masses are very close to being in antiphase, it looks, as their peaks and their valleys correspond with each other. And we see one amplitude is much higher than the other for the x1 and the x2. They are both oscillating at both natural frequencies as we go forward in time. So that's just their position versus time. Let's look at the animation to visualize what this is going to look like. Right, so here they are bouncing in, again, it looks like antiphase of each other. I'll run it a second time. So they're coming together at the same time, and then they're pushing apart at the same time. So going back to the work that we did, we found our total solution for x1 and x2 of t as a vector equation here. They are both oscillating at both of the two natural frequencies. But we started with modeling the system, finding its kinetic and potential energies, using Lagrange's equations to develop the two equations of motion as scalar equations, and then combining them into the matrix equation of motion. Identifying here a mass matrix and a stiffness matrix. There was no damping, so there is no C matrix here, and there's no forcing, so the right-hand side is the zero vector. So we identified it, and we saw that this type of system has a solution or a trajectory x of t that is going to be dependent on the first natural frequency and the first mode shape, plus the second natural frequency and the second mode shape, and it's going to be these two cosine terms. So for the parameters, we found the natural frequency and the mode shapes based on the M and the K matrices using their eigensystem. The C's and the P's, we had to apply our initial conditions and solve 4 simultaneous equations to find the C's and the P's that made them all true at the same time. We did that numerically using fminsearch in MATLAB, but there are other techniques you could use as well. But it satisfies the 4 given initial conditions. Now, knowing all the parameters, we can put them together and assemble our total solution, which we then were able to plot.